So what I intend to do now really is just to say a few words about some further developments in the framework model that Jan and I developed, where it's going. Some of those are things that we've developed more recently than the information in the previous talk. But it's work in progress. Some of these will also be to do with ideas that have come about from discussions here. It's going to be, well, I'll move it onto the screen where I say precisely this. It's going to be rather speculative in terms of we don't really know any results. So there are some results up there that look like they might be right. But if there's anything up there that you think, well, that sounds ridiculous, then, well, maybe it is. So I'll just run through some thoughts about these things in general, and well, I'll say more as we go. So there's just a few different topics about how things have developed really. So it won't take the full length of the session that it's been given probably, but I say that and then I waffle on and we find that we do take the time, but I probably not this time. So let's see the first of these different topics. So previously, when you've seen with the framework we had, there are the three key elements. There's what's the structure. So there's a population structure in which individuals move around and can potentially play a game. There's what games we play, so potential multiplayer games. And then there's a dynamics which follows the evolution of the population. So individuals gain a fitness by their various activities, and then there's some kind of updating. So it was only until the 2015 paper when we had a proper method of dynamics to do this, but it's only one dynamics. And so one of the recent things that we've been working on is getting a more complete set of dynamics to cover a wider range of potential scenarios. So this was the kind of thing that we had. So in the 2015 paper, we used a birth dynamics, and so what happens there is that an individual is picked for birth proportional to its fitness, and then it kills one of its neighbours in inverted commas. So in an evolutionary graph theory, a neighbour is obvious. It's an individual that's connected on the graph, and you can have different weights, but typically those weights that they're equally weighted. A neighbour in our case is someone who you're likely to be able to meet within the different group formation. And the more likely you are to meet someone, the more the stronger the weighting and the more likely you are to replace that particular individual. And so these were the particular weights that we used. So we think about the group. So the weighting of you replacing me is just looking at all the potential groups that you and I can be in and seeing how likely we are to meet. But also we weight it by the fact that there might be others in the group and you're only going to kill one person, and if there are 20 others, then it probably won't be me. If it's just you and me, then it will be me. And so the actual size of the groups also factor in here. And so you'll notice here there's a Dij, and here there's a Wij. In the original paper, this Wij was actually just Dij. And indeed, in this particular dynamics, these two things will be precisely the same. But in general, in the dynamics we're going to look at, they won't always be the same. And the point is, this is just a measure of how you and I are related to each other, how strongly we are connected. And then within that, we will then update the population based upon the different potential connections that any pair of individuals can have. And here's a complete set of dynamics. So these dynamics are effectively, so what we were trying to do was to get a system that worked in the same way as in evolutionary graph theory, to have the full potential set of behaviors that exist in these different dynamics. So remember before, for well-mixed populations in pre-evolutionary graph theory, it didn't really matter when you thought birth was first or death was first, or whether fitness operated on the first, selections operated on the first move or the second move. All of these things were pretty much the same thing. And that's why not much thought was given to this. Here, we've now got 6 potential dynamics. So this, called the birth, death, birth, what this means is that birth happens first. So I give birth, I kill someone who's my neighbour, and this B here is selection acts on the birth activity rather than the death activity. So this guy, the individual giving birth is picked proportional to their fitness, and the individual killed is just at random. So at random, depending upon the weights, but it's nothing to do with the fitness. And so birth here depends upon fitness. For fitness of all of the individuals, this is the fitness of the particular individual chosen, and so it's proportional to this individual's fitness, and then it kills one of the neighbours at random. And you'll notice here we've had this Wij divided by the sum of the Ws. With the particular weights that we've used in the previous set, this sum of the Win I've written here, is just 1. So the D and the W are precisely the same thing. You could define a different set of weights following some different rules where that's not necessarily the case, but it's got to kill someone, and so we assume it's got to kill someone. Maybe it hasn't, but the standard thing is you're always going to replace someone, and so then it's just proportional to the weights. There's a set of different versions. So birth, death, death. Birth happens first at random, and then death happens proportional to inversely proportional to fitness. So here, birth just happens at random. I just pick an individual and it gives birth, and then it kills someone else. But the one it kills is depending upon the fitness of the individuals, and it's proportional to the inverse of the fitness. So the worse they are, the more likely they are to be killed. And so this just reverses those two. So this is death happens first, and either selection happens at the death time. Here, selection happens at the birth time. Again, death is happening first. And these two are what are called the link dynamics. And in this case, instead of picking an individual to give birth, I pick a connection. So I pick a relationship between a pair of individuals, and these two individuals, one of them is going to replace the other, and selection happens then depending upon here the link is proportional to the individual doing the killing. Here the link is proportional to the guy who's being killed. So there are 6 types of dynamics, and we've done a little bit of work with some of these, but not a lot. The main thing: establish the dynamics, show a few results with it, and that's about as far as we are so far. So what we've done with this, or in the process of doing with this, and in particular this is work that Karen's immediately engaged in. So we can think about a population which is going to be this time is going to be represented by a graph, but this time the vertex is not just one individual. It's going to be home to a subpopulation of individuals. There might be 2, there might be 100, there might be none. So these can be empty. So standard evolutionary graph theory, one vertex, one individual is what happens, or you might have versions where it's one vertex and a fixed number of individuals, but not typically evolutionary graph theory models. But here what we've got is a variable population size, and the population is effectively going to be a network of well-mixed populations. So within the particular population, we're all effectively the same. So there are 7 of us sitting at this vertex, and our behaviour is going to be indistinguishable. We don't actually always have to go to the same place. All it means is my distribution and your distribution are the same. So I might go to the left and you might go to the right, but our behaviour is the same, and our behaviour in particular is different to the guys over there. And so it may well be we have a real well-mixed population, a strongly some kind of strong mixing in the population, so the group sizes don't have a big effect. But it might be that we're very, very specific to certain places and we don't move much, and then the group size can have a very big effect. The group separation, the subpopulation can have quite a big effect. So they can have any size up to 0, and we're going to be interested in the impact of how these subpopulation sizes how different parameters, how well they mix affects certain properties. The only one that I'm going to mention here is in a multiplayer public goods type scenario, how cooperation evolves. But because we haven't really looked at too many other things. Really, at the moment, we've only thought about multiplayer public goods, multiplayer Hawk Dove in these kind of games. So, and you can obviously see that there's some connection to island models. Typically, within island models, behaviour happens within the islands, and there's migration between the different processes. The way we do it is going to be rather different and more in the spirit of how evolutionary graph theory operates. But there's flexibility to behave differently, but we haven't done so far. So this is in our standard picture that we put up, where we have individuals that are linked to places. So here I've got 5 individuals, and they're linked to 3 places, and each of these individuals, so this is the standard picture, so each of these individuals has their own distribution. Within here, you'll notice I1 and I2 have the same set of places they can go to, and what's not written on here, but which is implied by what the structure on the left, is that the distribution of I1 and the distribution of I2 are exactly the same. So if these probabilities are 2/3, 1/3, so are these, 2/3, 1/3. And then I3 and I4 also have the same set of places to go, and again their distributions are the same. So you can think of these two as one particular subpopulation that have a certain type of behaviours available to them. There's something that links them that means they're the same. And so they're written I1, I2, and similarly I3 and I4, they're also the same as each other in terms of distribution, and I5 is its own separate population, and I can identify these with particular places. So in some kind of one version of the model, we can identify these individuals with one particular place as a home. These can have a different place as a home, and this one can have a different one, and there might be several places that don't have anyone who regards it as a home. But it doesn't have to be like that at all. So there's not necessarily any particular place these guys are associated with, though in the thing that we've looked at so far, there are. So we have individuals of a particular subpopulation that live on place PM. So QM lives on place PM is the default, but it's not the default. It's the one that we've looked at. And this is the type of game that we've considered. So this is the one that we used in this 2015 paper. It's a variant of a public goods game that people have played before. The only thing that's, well, I'll say how it works, and then I'll say what's different about it. So, or what's a particular feature of our model which may or may not be different to other people's models, and I'll explain why it may or may not be different. So what we have in this game, everything is scaled for a start. So in a normal public goods game, there's a benefit and there's a cost. Here, the main thing is just the ratio between benefit and cost, so everything is scaled, so the cost is 1. So this guy is a cooperator and always pays a cooperative cost. So it may well be that, and this individual, this is an obligate cost, so it has to pay it whoever's around, and indeed whether there's no one around. So this is an individual that maybe it's a bacteria in a particular medium, and it will just give out some chemicals, no matter who's there. So this is the feature that I'll come back to as to what happens when it's on its own. But in particular, this guy is a cooperator, so it has to pay the cost, and within a group of A cooperators and B defectors, it will receive this reward. So it doesn't receive any reward from itself, but it receives a reward from all of the other cooperators. There are A-1 of those, but that needs to be, so each cooperator's reward needs to be shared between all of the other individuals in the population. So there are A plus B minus 1 other individuals, and so every individual, every cooperator's contribution is 1 over A plus B minus 1 times the benefit, and so there are A minus 1 of these. Another version would be that maybe I'm allowed to share my own contribution, and so it would be possible to change this to A divided by A plus B. There are scenarios when one is better and the other is better, but this is the one that we picked before, so we thought no particular reason to change it. This is the defector. It doesn't pay any cost, so if there are no cooperators, it just gets nothing, and if there are some cooperators, then it shares their reward in a similar way. And here, it's not one of the cooperators, so it gets all the reward. It gets 1 over A plus B minus 1 for all of the A cooperators that there are. So as I say, here, the difference, one key feature here is that if I'm on my own, I pay a cost of -1 without getting any reward. I said this, that it may or may not be different to other people's usages, because almost all cases where these public goods games are played, the situation where you're on your own really isn't considered. So normally there's a fixed group size of individuals, and so it's defined for K individuals, and you can see that the definition extends to different K, but it's not really assumed, it's not really stated what happens if you're on your own. There's a couple of notable exceptions, but again, with there, something slightly different is happening. So Christoph Howatz and colleagues considered a situation where there was a loner strategy, and where individuals would actually actively go to be alone under some certain circumstances. But again, that behaved slightly differently. And so we've assumed here that effectively our individual is just paying a cost on its own. A variant would be that it doesn't pay the cost if it's on its own. So it would only pay a cost if there are some other individuals around. I'm not saying one game is better or worse than the other, but we picked this one. So following this, we consider various populations on a graph and how they evolved. I'm not going to put any figures up with this particular example. I'm just going to make a few comments. So what we did, we considered a complete graph, so the complete graph of populations. So each population was potentially equally connected to each other, and that meant every individual could potentially go to every different position, but they would have different distributions of doing so. And in particular, they were mainly attracted to one place, which was their home, but occasionally they went to other places. Occasionally, sometimes a lot, but each of the other places were treated as other places to go, and they would have a different preference for being at home to being somewhere else. As often the case, only these two dynamics seem to allow cooperation to happen in these cases, and this is a common feature of a lot of the evolutionary graph models. And the key feature of these cooperating populations was the existence of stable and small groups, subgroups, what helped cooperation to happen. So what I mean by that is, within our movements, we would, to be stable, we would need to stay at home a lot relative to moving around. So if I pick every place with certain probability, then I don't see my group mates that often. And so my group is stable, may be the wrong word, tight rather than loose, I guess is probably more what I mean. So that the group will always come back together, but they'll spend a lot of time with the other guys, and that's not going to help the cooperators. What was particularly clear within the model is that the small was also important, and that the more efficient cooperation happened when group sizes were 2, 3, 4, 5, not 10. And so the bigger the groups, the kind of worse, the harder they found it to keep together and not mix with the defectors. So lots of small cooperating groups behave better than one big cooperating group, because the group wasn't so cohesive, and it was easier for defectors to get in with the mix. One of the things that comes on from this is, in the previous paper, we developed an idea of temperature, And temperature there was a measure of how much replacement of a particular vertex, a particular individual would happen. And so in that circumstance, I would be high temperature if there's a lot of chance of this individual being replaced by something from outside. And so there were some nice results based upon temperature. There was a strong correlation between temperature and how well cooperators did, how well defectors did. That's also true here, but we need to be very clear about what temperature means. There is the same thing as subpopulation. All the subpopulations were size 1. So their temperature of the vertex and temperature of a particular individual were the same thing. Here, so here, temperatures need to apply to the vertex and the individual separately. So for instance, if I have a big subpopulation, lots of different individuals, if I'm replaced by someone within the same group, then that affects one temperature and not the other. And in fact, it turns out to be the vertex subtemperature that's the important thing as we're developing. But that's work in progress, but I think that result is already clear to us. So that's as much as I'm going to talk about that particular one. So I'm going to say really a few things which, as I say, these statements have a health warning, so that when the papers come out, then it may well turn out that something slightly different is said when we realise that what I've just said is wrong. So let's move to the next one: strategic movements. So this paper has been submitted. So hopefully these statements are true. So here, again, we're assuming all individuals have no knowledge of the choices of others, and so they move independently. And here they're going to follow the independent model before, so everyone picks a distribution. And so this is back to the original case, but this time individuals are selecting their movements strategically. So actually that mirrors what Jan was getting you to do on the program, and what he was talking about with the game in his talk. That there, the strategy selection is the key thing. In this particular paper, what we're doing is proving some particular results under certain circumstances as to what happens in this kind of case. So here, the game at the end of it is a trivial one. Sometimes you can have movements that are strategic, and then when you get there, also the game is strategic. I don't like doing two difficult things at once. So in this case, when we get to the end, it's just a very, very simple game and there were a couple of main alternatives. The ideal free distribution of habitat selection idea, where when you get there are just resources to share, and you just all share the resources. And the other one, the alternative, was what's called predator dilution case, where just when you got there, someone came along and ate a random individual from the group. And so, okay, that's not true. When everyone dispersed, a predator would pick a random place, and then it would eat a random individual from that random place, if there happened to be anyone there. So the question is, how do these individuals select their moves, and what distributions are stable? So fitnesses of individuals only depend upon the size of the group. So for foraging scenarios, small groups are best. So this is the habitat selection. So if there's some food there, the fewer competitors I have for it, the better. For games involving predation, large groups are best. So if a predator is going to eat one of us at random, I don't want to be there alone. I'd like there to be lots of us there. So the individual it eats is unlikely to be me. And there are other scenarios where there'll be some intermediate size that's best. So for instance, there might be some kind of a Lee effect or whatever, whereby small groups are bad, big groups are bad, and there's some kind of intermediate effect, or indeed the other way round, or something more complicated. But the key thing is, we know pretty much what the results are likely to be for well-mixed populations. What's going to happen when there's some structure that's going to limit where individuals can go? And so some particular results. So if the smallest group size is optimal, then for well-mixed population, we just recover the habitat selection game. So effectively, this is just a finite version of the habitat selection game that results are already well known for, and there are nice mathematical proofs for the continuous case, we've got a version with that for this discrete case. However, if there is some restriction on individual movements, this turns out to be more difficult, and so you can't prove, well, you can't prove uniqueness. There isn't uniqueness, but you can show some certain things. I'm just going to put up this one slide and say something about it for 30 seconds. If the largest group size is optimal, then we've got a way of generating all of these stable collections. If the population is well mixed, it doesn't matter. Well, depending upon how your places are designed, either it doesn't matter where you go or it's one particular place is best. But the answer to that is easy. When there's structure, then the answer isn't necessarily easy, but we've got an algorithm that we've proved that you can find all of the different cases. For intermediate group sizes, it's more complex. Namely, okay, we can't really prove anything for anything general with an intermediate optimal group size. So these are either for minimum, smallest is best, possible is best, biggest possible is best. So intermediate versions is tougher. So looking at this figure, this is just a case where this individual can go to these two places, this one can go to these two, this one can go to these two, and depending upon a particular ordering, then different kind of things can happen. So in case A, these individuals happen to have gone to these places, and here we've defined this particular set of values. So this R21 means, so all of these individuals are deemed to be equally hungry, able to eat resources. R21 is the value of place 2, so when there's one individual there. So R22 is what resources are there, what the value of it, if there are two individuals there. And so we picked this particular ordering of events. So if these individuals happen to be distributed on these points, then that's stable and no one can move anywhere else. The only move would have to be either have individuals 2 at a place, which would be worse, or this one would go from there to there, which would be worse. And similarly in this place, you have an alternative set of movements, and so this one is stable. Figure C actually is slightly different in the sense that this is saying it shows an order under which no stable occupancy is reached. What we really mean here, I guess, is that what we wanted to do was be able to say, well, let's find an algorithm for finding this, and let just individuals pick places in order. Here, if individuals pick places in order, something goes wrong. And so it's possible that you just so an algorithmic way of doing this, you would find something that would mess up. But the key feature is that there's multiple solutions, and as you have this is a trivial example, of course. When you have many cases, then all sorts of things can happen. So those are two ideas. Let's have a look at non-independent movement. So at the moment, everything has behaved like this fully independent model. So here we've got a case where movement is going to be not independent and identically distributed. It's going to depend upon our history, which was the whole point of the general framework at the beginning, was there was the flexibility to do this. But we've not really done anything on this apart from what we're going to say now. Though actually the methods that Jan has done with the computer programming mirrors this kind of thing, because the individuals will be working out what to do based upon where they were before. But in a theoretical sense, so we've not really done anything on this kind of behaviour. So here we're going to have an individual that depends a population where behaviour, where they go, depends upon where they were last. So, I mean, in general, it could depend upon their whole history. But here we're going to consider, so this PNMT, this is the probability that individual N goes to place M at time T. It might depend upon the whole history of the population. Here we're going to just depend upon where the population was last. So there are three potential, well, three, there are more than three, but there are three things that I can emphasize. One is maybe it's the case that these individuals don't move independently, so the population moves in some sense, so you can have a cohesive set of groups of individuals that move around this place, and some of them will stick together. So there the individuals wouldn't move independently. But they would depend upon the whole population. That's not what we're looking at here. We're picking something slightly simpler. So each of these individuals move independently, but they move independently dependent on what the whole population did, or at least some knowledge of others apart from just themselves last time. It's possible to have a simpler case again, where I am only interested in where I was last, so I didn't see where all the others were. So I run around the place, but I run around independently of where everyone else is. So that's a simpler case again. We're going for the intermediate case where current movements are independent, but they depend upon a collective history. And so what our individuals do, we play the same public goods game that we had before, and this time we see where we are. So I see what's in the group, and I look who's in the group, and then I make a movement depending upon on what's happening in the group. So I look at how many cooperators I've got and how many defectors I've got with me. If I've got a lot of cooperators and not many defectors, then I like to stay where I am. If I've got a lot of defectors and not many cooperators, I like to move. And that's true of both cooperators and defectors. Cooperators like to be with cooperators, but so do defectors. Cooperators don't like to be with defectors, nor particularly do defectors. Actually, it doesn't make so much difference in our game if you're a defector, whether you're with other defectors or not, if there are no other cooperators around. But in any mixture, adding cooperators is good, adding defectors is bad for both types. And so we depend upon this and we make our moves, and individuals can then have some number of group mates. If they've got lots of cooperators, they'll stay. If they've got lots of defectors, they'll move, and then they move around. So one result we've seen is that fast movement enables cooperators to find the other cooperators, which is good, but it also enables them to be found by defectors, and slow movement prevents cooperators from finding other cooperators. And so there are good things and bad things about being too fast or too slow. And indeed, it turns out it might be the case that defectors and cooperators want different speeds of movement, and we're thinking about versions where there's some costing involved. But here's a figure, and this just says, so this is where they both have some kind of measure of speed. So this alpha is, a big alpha is you hardly move at all. A small alpha is you move a lot. And so this is a fixation probability of a cooperator in a defecting population. This is the fixation probability of a defector in a cooperating population. And this is the baseline 1 over n. And you see that here the cooperators do badly if things are too quick, because the mixing is too much. You see a lot of defectors. They do badly if the movement is too slow. They can never coordinate with other cooperators, and they always pay this cost at the front, so they're suffering compared to lone defectors. But in intermediate values, the cooperators can do well. And so we've got a few figures that look a bit like that, but again, this is in development. So let's have a look at just some thoughts. So first, this little section is going to be some thoughts on what kind of real populations we can apply the model to. Then the next section is going to be maybe some developments on this, on some thoughts that have happened based upon discussions that I've and colleagues have had here, and then a few conclusions towards the end. So what kind of applications might we have? Well, the most obvious is the one is to do with animal territoriality. So individuals in populations that are individuals in populations that move around somehow, but also that there's some kind of structure to their movement. So there are some places where I like to be, some individuals that I might like to be with, some in places I don't want to go, or individuals that I don't want to be with. And so this is the natural extension, I think. So we could consider boundary conflicts or incursions into territories of other individuals, of other group, and this is the understanding of what the territorial radar model is about. Alternatively, individuals may just travel to different places to forage. So we've got a place where we start, and then we go and forage somewhere else. And when we're foraging somewhere else, we're interacting with other individuals, and maybe maybe we're just competing against them, maybe we're actively stealing off them, and so on. So, but that's this kind of scenario where there are these different kind of places and multiple interactions is what we're looking at. So here there's a clear representation of what our structure means in terms of a physical location. And so movements are physical movements from place A to place B. So if you've got short-term movements where I've got a den or a roost, then this independent model is quite reasonable. So then I start here I go out, do a bit of foraging, and then I come back, and then the next day I do the same thing, and so on. So I have effectively the same set of distributions available to me. But the wild dog example that I mentioned before, this is probably true for when they've got pups in the den, but after that they really run around everywhere. And so there, it's not reasonable to have that independent model because they move from place to place. And so something, at least Markov, would be required so that I would have to think about where I am now and where I move next for each of my different interactions. Though they again will return. Yeah. Okay.
I was just wondering if it's so what we're talking about here is two very different movement modes, right? Where the animal is moving away or from its central place and it's kind of been traveling or one we can better than exploratory sort of phase versus when it's foraging and now it's kind of encamped in that area and trying to acquire things before we engage in exploratory movements. So does that mean that would it be feasible to have sort of two different models that are operating sort of in sequential fashion to determine where the individual is going to move as a function of trying to satiate whatever it is their need or trying to give them direction?
Yes, I mean we try to keep life simple, but I mean to match something that's real, then we need to build in these kind of things. I mean, one of the things that we do with the Markov model at the moment is we kind of assume this wild dog at the den idea is that they run around and gain their fitness, but then they come back to a home so reproduction always happens at that place, and then they go out again. So the population always comes in, and then reproduction happens always at that point. Though it doesn't have to be like that, and there's some work that Jan and Igor have been working on where they don't do that, where reproduction happens as they're moving round, and so the individuals do something slightly different. So the structure doesn't, so they don't go back to those positions each time, and it depends upon what scenario you're thinking about. If you are actually at that stage thinking about any specific scenario, I think in either of our cases. Neither of us were thinking, okay, this is the concrete biological scenario, and therefore we'll certainly do that. It was just felt like a natural way to behave in each case. But yeah, to engage with a real thing, then we need to take into those factors into account, certainly. So that's. Okay, so the point is one of the things here is that our structure is some kind of physical location, and then we need to think about our different types of movement. So an alternative idea, we've not really done anything on this, but I've had a chat with Joel Brown, who's an expert in this kind of cancer modelling. Well, actually, he's an expert in two different things. Well, he's an expert in more than two different things, but these two specifically different things is in ecology of animal populations, particularly rodents, and in the modelling of cancer. And in fact, the methods that he uses for these cases are actually pretty similar, because he treats cancer as a population. So it's an evolutionary process where the cancer cells are individuals where they compete in a population, and cancers have got quite complicated things where there are different types within any particular tumour, and these can be thought more logically, pretty logically, as a population of individuals, each which are trying to survive. So Normal human cells do not behave like this, but there are lots of but cancer really does behave like this kind of population. And so in this scenario, the population structure is the environment is the human body, and so the population within that are moving or potentially not moving. So there's some movement, but there's some spatial interaction. Are the cells themselves, and of course there'll also be some external event of human control of treatment that will change the parameters and will change maybe the balance between some types of cells and others. And so these models are well established, is an exaggeration. I think well established within the evolutionary literature recently. Some medics are certainly taking this kind of thing on board. But it's a newish science, but there's some potential way that our models could potentially be come into play. But again, this is extremely early in the sense that this is a result of discussions, and no work at all has been done on this from our point of view.
So what's his name again?
Joel Brown. He's at Chicago.
What?
UIC, University of Illinois at Chicago. So here's another potential scenario. So interaction of groups, but here it's the interaction within groups. So I'm not talking about a population moving around places. Here we've got a population where there's some social relationship, maybe a dominance hierarchy, and actions are taken related to positions in the hierarchy. So if I'm at the top, there are different things I will do to if I'm at the bottom, and that will take me to interact with some of the others. So maybe the dominant individuals, the top guy will defend against those that are close behind, and so they will interact with each other in different ways than they'll interact with the ones at the bottom who are not making any kind of challenge to the top. And so the places, so the movement represents these interactions between these individuals. And again, depending upon what kind of population you've got, the model will be different. So if I've got a static structure of permanent relationships, so there's always a top guy, there's always a few in between, there's always a few at the bottom, then you can think of an independent model that basically the same kind of interactions happen over and over again. But if you have evolving relationships, societies that behave more complicated ways, then that's not enough. So if a particular change suddenly changed the nature of the hierarchy, so that now there's two guys at the top, or some different distribution, then something more complicated would be required. So those were a few thoughts that I'd had prior to coming here, and some of these feed into those. So one of the things that we discussed here, I mean, again, this is a thought that we'd had, but it's a thought in the sense of oh, that's a thought, but we haven't really done anything about it yet. From the point of view of discussions with some of you and comments, it seems that there are other things that we might be wanting to look at rather than, I mean, our bog standard, what's the fixation probability from this particular case? So that kind of slide where fixation of A and B, fixation of B and A compared to 1 over n. Particularly if you have large populations and the kind of games where there's some kind of equilibrium, so hawk-dove kind of games, but anything where the population mix will not evolve until a very, very long time to fixation of one type or another, we may well be looking at an equilibrium, and I say a quasi-stationary equilibrium, I always think of in terms of I want to solve this using a Markov chain kind of model. I want to solve it to get a proper stationary distribution, and of course, even if it will be several times the length of the universe before it gets there, then if I solve it in those kind of manner, I'm going to identify extinction of these guys, extinction of those guys as the final positions. So if I can condition against those, we can get a nice, and that's effectively what you'll get from a simulation of these kind of things, provided the numbers were big enough, you'll get some kind of quasi-stationary equilibrium. And there the key factor is, what's the proportion of this type compared to that type? So if I invade this population, do I get to 2/3 of me and 1/3 of them, or do I get to 1% of me and 99% of them? So my measure of success is how many of us there are. And so the measure of success will be different in these kind of situations. And yeah.
I wonder if it's not possible that, starting from a population of, say, all doves, a hawk has some probability of establishing in the population to get to a point where it all now moves to
The quasi-station, yeah, so, yeah.
I wonder if there's a possibility that even though the equilibrium is, say, hawk biased, the
Yeah.
establishment probability of a dove is higher than that for hawk.
Yeah. We could think of, yeah. Well, okay. So an establishment probability, yeah. So is maybe a probability of reaching some kind of minimum threshold or surviving for some particular length of time.
At which point selection sort of becomes deterministic.
Yeah. So yeah, I mean that's certainly indeed an alternative property, and maybe even be a better property than the one I've got here. So within any particular place, then we may evolve to some kind of long-term mixture, and then we might, of course, if we really do stay there for a long time, we might be interested in potential invaders from yet another guy coming from outside. Which normally we ignore because they're very slow. But of course, if you have a stable equilibrium, then suddenly there will be time for a third mutant to come in potentially. And so we could also consider correlated things. So like when Jeremy was talking about. So it may well be that what I'm really interested in is the probability of cooperation, but that cooperation, these individuals aren't all cooperators. There are different types of traits, and these each have different cooperative possibilities. And so there might be some thing that's not just number of individuals that I'm interested in, some general property that will come through. So a couple of biological examples that I was talking to a view about. So Garrett is interested in some wild pigs, and well, why are these wild pigs different to the kind of thing that I was talking about before, where these populations run around? Well, for his wild pigs, the pigs don't move particularly. Well, they move a bit, but the main thing that moves is people move these pigs around for hunting reasons, and so their movement isn't particularly geographical. It's not a pig runs from there to there. Someone sticks it in a van and drives it from there to somewhere else with the spaces in between ignored. So then there's a kind of different spatial movement, and these kinds of things would yield something slightly different to the things that we were thinking about, where individuals have to run around. And so there the graphical structure would be more than just a lattice, for instance. And talking to Caroline, had got a system with plant roots, and in these kind of systems, then the plants are staying where they are, but they're sending roots into the neighbouring regions, and even quite long distances. And if it's difficult to do that, then they don't grow many roots, and they stay at home. And they effectively just use their own space, and so they don't need to invest in all these roots. But when it's easy to compete, then lots of roots can be produced, and you can have some mass fights. And this really, I liked this system because this is almost the same as the kind of the Army territorial raider model that Jan was talking about earlier, where you have a number of units, and you send your units to fight in other places. And if there's a cost to sending them, then they all have to stay at home. But if there's a big cost, if there's a small cost, then you can run around. So Jan's army didn't have any cost, and I think the costs would have significant effects on these. So again, these are two I think nice examples to potentially follow up. So other things we talk about was making some parts of our framework maybe less stochastic or non-stochastic. I don't quite like non-stochastic. I think some probability in these is natural, but maybe with less stochastic behaviour. So some of the the models we heard about, Sergei's in particular, the groups were fixed together, and so that and so not only his, but and so here you would have within group and between group competition, and so our framework has the possibility of individuals running around collectively, so there'd be strong correlations between them, and the more coherent the groups, the less the potential of splitting, the more you'd get this within and between group competition situation. I mean, already that's how cooperation happens on evolutionary graph models, and indeed in our early models, is that our structure means that the cooperators tend to mix with other cooperators, defectors are mixed with other defectors. And that's why within these more fixed populations also cooperation can occur, because you can force the defectors to interact with other defectors rather than interact with other cooperators. Also, some of our dynamics could be, well, I say non-stochastic dynamics. So Paolo was talking about tipping points. I wouldn't like to go through the model where there was no stochastic behavior at all, but it could well be that the stochastic element was limited, and so that really there was almost no chance of anything happening until there was a large number of individuals around. And so this again is something that we could potentially do. So just some final conclusions, and I note I've done the same as usual. I said, oh, it won't take me very long, and here we are, almost 11:45. So let's have a look at a few conclusions. So we've now developed a range of factors into our framework, which we didn't have before. So about a year or so ago, what we had was a single dynamics, a method of a general method of doing all of this stuff, but without actually having concretely said how we were going to do it. So we had one dynamics, some games to fit in, and structures, and the only structures we'd considered were these independent structures. Now we've got some subpopulations, we've got some strategic movements, so the movements of the individuals themselves are their strategies, and we've got some history-dependent movement within it. And so now we're starting to get enough to start looking at things that are potentially more realistic. So I emphasise the word start, but this does potentially open up a range of applications for us to at least think about. And these are, well, the kind of things that I've just talked about. And there are a few more things that we could think about that have come directly from the discussions we've had. So different evolutionary properties to follow, apart from just fixation probability, fixation time, which is the ones we've principally looked at. Different types of spatial models, different types of ways of thinking about groups, and so on. And so, I mean, not necessarily that the way that some of the ways of thinking about the groups is particularly different to what other people have done in many times in the past, but it's something that we've not really thought about in this conjunction, just because it comes from so at least an evolutionary graph theory kind of mentality. So this is the finish. So we're going to continue working on this. In particular, there are those couple of models with the groups and with the Markov movements that are in train, and hopefully will completely crystallize relatively soon. So that's what we'll be doing. But we hope also that some of you are interested in these ideas, and also of those of all of the speakers of the workshop, and hopefully some of you will actually use some of these ideas in your own work, and we'd be particularly interested to hear about any of these examples where you actually do it. So anything where you're using this kind of stuff, please do tell us about. And well, it's still early stages, I guess, and so also any ideas about what we could do to make things better would also be welcome. And that is as far as I want to go, so I'll stop.